Hello, welcome back to this lecture series on quantum chemistry. In the last lecture, I was discussing about particle on a sphere model, particle on a sphere of constant radius. We derived the expression for, we started the derivation of expression for the wave function, and we stopped the last lecture at this stage. Okay, so I told you this is what we call as associated Legendre differential equation. Now we need to find out the solution for this equation. Okay, and we also should know what is the exact value of the lambda. Okay, yeah. So how to proceed? Okay, let me just focus on equation number 8. I told you both these equations are one and the same. Okay, instead of theta we should put p, that's all, right, where p denote Legendre function. Okay, before begin with, see here we have 1 minus x square term in the denominator, okay, in equation number 8. So we know that the range of x is, okay, what is the possible range of x? X, last lecture I gave this point, x can go from -1 to +1. Okay, this is the range for x. So if x approaches -1 or x approaches +1, x approaches -1 or +1, x square, okay, x square is a square of this, will approach 1. Okay, when x approaches -1 or +1, x square approaches 1. What happens if x square approaches 1 here? See here in equation number 8 or 9, whatever it is. If x square become 1, 1 minus 1 becomes 0. You know very well something by 0 is infinity. So the function, right, function diverges. Okay, it goes to infinity. Actually the function should vanish at x equal to -1 and at x equal to +1, because these two are the termini. Okay, this is one terminus, this is another terminus. So at the extreme point the wave function should become 0. Okay, but here the wave function diverges because it goes to infinity. Therefore, to get an acceptable function, so here the trouble comes here. Okay, so to avoid this trouble, okay, to get an acceptable solution, what we should do, okay, what we should do is when x square approaches +1, okay, we should make this term, that is m square into theta or m square into pl, ml square actually, into in the place of theta I'll put p. So m square into p, that should approach 0. If this approach 0, yes, this part becomes 0, you'll get a valid differential equation and you'll get a valid solution. Okay, the function will appear as a well-behaved function. Okay, so so this is what we need to do. When x square approaches 1, this quantity should approach 0. If this quantity approaches 0, means either ml should be 0 or p should be 0. Okay, either ml should be 0 or p should be 0. Here, yeah, you know the value of ml. ml can take value 0 plus or minus 1 plus or minus 2, etc. ml 0 is allowed value, but ml non-zero values are also there. Therefore what we need to do is we need to focus on the function p such that p should approach 0. Okay, so what is our goal is, as x square approaches 1, p should approach 0. Okay, so how to do that? For this purpose, let me define the function p of x in this manner, that is 1 minus x square power alpha. Okay, this is the function when x approaches +1. Okay, this is the nature of the function when x approaches plus 1 or minus 1, so that x square will approach 1. So at the extreme points, okay, when x approaches plus 1 or minus 1, the function should vanish. How the function should vanish? If the function behaves like this at x approaches plus 1 and minus 1, okay, what will happen? See here, if I put in the place of theta, if I put theta or p, whatever it is, right? If in the place of theta, I'll put this 1 minus x square into alpha. 1 minus x square alpha will be there, and I'll take this alpha should be a positive quantity. Otherwise, again problem starts. Okay, so I don't want to go into the problem again. So let me state that alpha is a positive quantity. So if alpha is positive quantity, if I put 1 minus alpha, 1 minus x square power alpha, here I have 1 minus x square. Okay, so if you bring it to the numerator, it will become 1 minus x square alpha minus 1. Okay, 1 minus x square alpha minus 1. Since alpha is a positive quantity, in that case, what will happen if x approaches, right? If x approaches 1, since this term is the numerator, okay, when x approaches 1, this part becomes 0, the function becomes 0, so this entire term becomes 0. Okay, therefore the equation becomes a well-behaved function. So the solution for p should contain this term. This term will take care of the function when x approaches plus 1 or minus 1. We don't know what is the nature of the function in between. Between minus 1 plus 1, we don't know. Okay, as x approaches plus 1 or minus 1, right, the function should behave like this. Otherwise, the function diverges. Okay, it becomes unacceptable function. So what I'm going to do, I'm going to define the function p of x such that it should consist of 1 minus x square power alpha term and another function q which will take care of the function between minus 1 and plus 1. Okay, so I am defining the function like this. Now I don't know what is the nature of this function. Let me find it out using differentiation technique. So what I'm going to do, I'm going to differentiate this 2 times and I'm going to substitute in equation number 8. Okay, so before that, let me define this quantity as f. F is equal to 1 minus x square into alpha. And I'll make some algebra here. So if I differentiate this, okay, if I differentiate this once, I'll get alpha into 1 minus x square alpha minus 1 minus x square and differentiation will give minus 2x. So you'll get minus 2 alpha x into 1 minus x square alpha power minus 1. Okay, or if I multiply by 1 minus x square, okay, both side, I'll get 1 minus x square of f dash equal to minus 2 alpha x. If I multiply by 1 minus x square, I'll get 1 minus x square power alpha. Okay, which is 1 minus x square power alpha is nothing but f. So this is minus 2 alpha x into f. Right? Keep these terms in mind. We will substitute this wherever necessary. Okay. Yeah. Now, so this is the definition. So I will take this as equation number 8. This is how I define the function now. Okay. We need to find out the function q. To find q, what we have to do, you have to differentiate this 2 times and substitute this in equation number 8. Okay. That's the idea. So how to do that? Let me write to the next page. So I'm going to differentiate this. This is become f. Okay. So p of x is now written as f into q. F is a function, q is another function. I'll differentiate this once. So dp by dx equal to keep f as such, or differentiate f and q, keep it q as such, then keep f as such and differentiate q dash. Okay. Then now let me focus on equation number 8. See this equation, in equation number 8, wherever theta is there, we should put p, that's all. Okay. In equation number 8, I'll take this term first. This is first term, right? I'll take the first term of equation 8. Right? So I'm taking the first term of equation 8, right? Which consists of dp by dx, okay, which consider dp by dx into 1 minus x square into dp by dx. Okay, 1 minus x square into dp by dx. This is the term we have. Okay, now I'll keep this dp by dx as such. I'll keep this 1 minus x square as such. What is dp by dx? We have differentiated here, which is nothing but f dash q plus f q dash. Okay, now I'll keep this dp by dx as such. I'll multiply this here. 1 minus x square into f dash. Yes, I have defined that. 1 minus x square into f dash is equal to minus 2 alpha x into f. Okay, so let me substitute this here. So if I multiply this 1 minus x square here, I'll get 1 minus x square into f dash, which is nothing but minus 2 alpha x into f. And we have this q. I'll keep that q as such. Then multiply this here. So I'll get 1 minus x square f q dash. Right? Now I'll differentiate this. Okay. Listen, here minus 2 alpha is constant. Keep it as such. Now I have three variables, x, f, q. Okay. So first I'll keep f and q as such. I'll differentiate x. If I differentiate x, I'll get 1. Okay. Then minus, now what I'm going to do, I'll keep 2 alpha x q as such. I'll differentiate f. If I differentiate f, I'll get f dash q. Now I'll keep 2 alpha x f as such. I'll differentiate q. Okay. I got three terms here. Similarly, I'm going to differentiate here. I'll keep f and q dash as such. If I differentiate 1 minus x square, 1 and differentiation becomes 0. Minus x square will give minus 2x. So, which will give me minus 2x f q dash. Then plus 1 minus x square into, I'll differentiate f now, f dash q dash, plus 1 minus x square into f. If I differentiate q dash, I'll get q double dash. Okay, so we have got this term. Let me simplify this. I'll write that q double dash first. So 1 minus x square f q double dash plus wherever q dash is there, see I have q dash here, q dash here, q dash here. Okay, q prime, which indicates, q prime indicates first derivative of q, okay, with respect to x. So I'll take q prime as constant here. So I'll get here let me write once, minus 2 alpha x f. I have taken q dash as common, and here we'll get 2 minus 2x f. Okay, and here we'll get if I take q dash common, I'll get 1 minus x square f dash, and we know already 1 minus x square f dash is minus 2 alpha x f, which is nothing but minus 2 alpha x f. Okay, so we have considered all the q prime term, then q dash, right? Then the remaining terms. What are the remaining terms? We have 2 alpha f q, the first term, and the second term, that is minus 2 alpha x f dash of q. Okay, yeah, we have taken into account all these terms. Now see here, minus 2 alpha x will give me minus 4 alpha xf. So I'll take that 1 minus x square into f into q double dash, okay, plus q dash, okay, minus 2 alpha x minus 2 alpha xf. If I add, I'll take f also as common. Okay, yeah, I'll take f common. So I'll get minus 2 alpha x become minus 4 alpha x. I'm sorry, minus 4 alpha x minus 2x. Okay, I just added these two and I took f as common. Then here you keep these two terms as such. What is that? 2 alpha f q, then minus 2 alpha x f dash of q. Okay, right. So we have got an equation up to that. Now what next? So we have to simplify this further. So what I'm going to do, I'll take next page. Yeah. Okay, now let me show how to simplify this further. Okay, see what I'm going to do, I'm going to substitute this in equation number 8. So what is equation number 8 now? Equation number 8. So instead of this first term, I'm going to introduce this. So which is 1 minus x square into f q double dash plus f into q dash. Here we have minus 4 alpha x. Okay. Here we have minus 2x. So if I take minus 2x as common, I'll take minus 2x also as common. So minus 2x f q dash. If I take minus 2x as common, I'll get 2 here, 2 alpha plus 1. Okay. And what about here? Plus I'll take q as common here. Okay. If I take the term q as common, I'll get minus 2 alpha into f. Okay. Then minus 2 alpha x f dash. Then the remaining terms of equation number 8. What are the remaining terms of equation number 8? Let me show you here. So these are the remaining terms, which is plus into lambda minus ml square minus 1 minus x square into, this is p. What is p? P is defined as 1 minus x square into alpha into q equal to 0. Okay. Yeah, this is our final equation, right? And this is nothing but f. Okay, you can also write f in the place of this. So this is nothing but f. Okay. So now what I'm going to do is that let me write one more step. 1 minus x square f q double dash, then minus 2x f q dash to 2 alpha plus 1, and here we have this quantity. Let me simplify this quantity before going with the other one. Okay, so let me give a point. Let me do a small algebra here. Just keep this carefully. Okay, just watch it carefully. See, minus, we have this term minus 2 alpha x f dash. Okay, and this can be written as, so this term, I'm talking about this term, minus 2 alpha x f dash, right? I can write this term as minus 2 alpha x. What is f dash? We know f dash is nothing but minus 2 alpha x. Okay, in the last page I showed that minus 2 alpha x into 1 minus x square power alpha minus 1. Okay, or you can also write this as minus or minus become plus 4 alpha square x square into 1 minus x square alpha by 1 minus x square. We can write like this. Okay, what is this? This is nothing but f. So 4 alpha square x square into f by 1 minus x square. We can write like this. Okay, we can write like this. Okay, we can write like this. So what I'm going to do, in the place of minus 2 alpha x f dash, I'm going to substitute this. Okay, so if I do that, what will I get? Let me show you in the next page. The derivation looks somewhat lengthy, but it is very simple one. Okay, now let me rewrite this function again. Okay, so this is our function. Okay, let me rewrite this function again. So what is that? 1 minus x square into f q double prime minus 2x f q prime into 2 alpha plus 1. Here in the place of minus 2 alpha x f prime, I am going to substitute this value. So now this become plus 4 alpha x square f. So we have one f term here, and here also we have f. So I am going to take f also as common. So if I take f common, I'll get f of q into, this become minus 2 alpha, and this will get 4 alpha square x square, 4 alpha square x square. We have taken f as common by 1 minus x square. Okay, so this is the term we have. Then we had the remaining terms. What are the remaining terms? This one, that is lambda minus okay, let me rewrite that once. Lambda minus ml square by 1 minus x square into f q equal to 0. Now see, we have f in all these terms, so you can divide throughout by f, okay, so that you can remove f there. So you'll get 1 minus x square into q double prime minus 2x q prime into 2 alpha plus 1. Here, yeah, now I'm going to make some more simplification here. See, what I'm going to do is that I'll write this term as I'm going to combine these two. I'm going to combine in this manner that we have lambda term. I'll put that as such. Okay, then I'll put 4 alpha square term, then this minus 2 alpha term, then I'll write the term like this: 4 alpha square minus ml square by 1 minus x square into q equal to 0. Let me write like this. Okay, yeah, listen, see, minus 2 alpha terms are there, lambda values are there, so we have to account only for these two. Okay, whether these two will give me that or not, how to check? Yes, let me show you that. See, we have minus 4 alpha square here, and we have plus 4 alpha square minus ml square by 1 minus x square. Okay, now what to do? Take LCM. If you take LCM, you'll get minus 4 alpha square into 1 minus x square plus 4 alpha square minus ml square whole divided by 1 minus x square. Okay, this we can write as 4 alpha square. You can take common, so 4 alpha square, if I take common, I'll get here I'll get 1, here I'll get minus 1 minus x square, so minus of minus 1 become minus 1, minus of minus become plus x square. I'll get a term like this: minus ml square over 1 minus x square. Okay, plus 1 minus 1 cancel. So what I'll get is that, let me write here, what I'll get is 4 alpha square x square by 1 minus x square, one term, and minus ml square by 1 minus x square. I'll get another term. See, now we got these two terms, this term, and this term, this term. So we can write these two terms, that is this and this, are replaced into like this. I have introduced a minus 4 alpha square and this term. Okay, that will take care of those two terms. Okay, so nothing wrong in it. Now see, let me make some more algebra here. Yeah, what's that? So now this is the equation. Let me simplify this equation further. What I'm going to do is, listen, here trouble comes when x square approaches 1. Why? Because if x square approaches 1, see here in this equation, if x square approaches 1, 1 minus 1 becomes 0. Something by 0 is infinity. If the equation goes to infinity, the function will also goes to infinity, it will diverge. Okay, we don't want the function to go to infinity, right? So we have to get an acceptable solution. For that, what I'm going to do, I'm going to make this quantity 0. 4 alpha square minus ml square should be equal to 0. Okay, so this is, so to get acceptable solution, okay, we should fix this 4 alpha square minus ml square should be 0, or I can say 4 alpha square equal to ml square, or we can write alpha square equal to ml square by 4, or alpha equal to ml by 2, but ml can take positive and negative value, you know. ml can take positive or negative value, but alpha is always positive, I told you. Therefore, we should take only the magnitude of ml by 2. This is the alpha value. So now we have identified the nature of alpha. Okay, so therefore the function, our original function p of x, okay, which is actually written as PL of power m x equal to 1 minus x square power alpha term was there. Now I replace this alpha by ml by 2 into q of x. Okay, so this is the function. Now we need to identify the q. To identify q, we should consider this equation. But let me first introduce that for this function to be valid, this should be 0. If this is 0, this term vanishes. Okay, so this equation will become, let me write here, right, this equation, I'm going to write this equation as, so 1 minus x square. What is q double prime? Q double prime is nothing but d square q by dx square. Okay, minus 2x into 2 alpha plus 1. Okay, we have 2 alpha plus 1. What is alpha? Alpha is nothing but m by, we found that alpha is nothing but ml by 2. So if I put ml by 2, 2 cancel, I'll get ml here. So I'll get 2x into modulus of ml plus 1 into q prime. Q prime is nothing but dq by dx. Okay, then plus we have this term becomes 0. So I have lambda minus, I'll take 2 alpha as common. Okay, if we take 2 alpha as common, I'm taking minus 2 alpha as common. So this become 2 alpha and this become plus 1 into q equal to 0. So this is the function reduced like this. Okay, and in the place of alpha I'll put ml plus ml by 2. So I'll get 1 minus x square into d square q by dx square minus 2x into modulus of ml plus 1 into dq by dx plus lambda minus, in the place of alpha I'll put ml by 2, 2 cancel, so I'll get modulus of ml into modulus of ml plus 1 into q equal to 0. Now for further derivation, see every time writing ml, okay, right, is somewhat little tougher. I don't want to avoid that confusion ml and all. So let me replace ml as m simply. At last we'll put ml in the place of m. Okay, so what I'm going to do, right, so this equation now becomes 1 minus x square into d square q by dx square minus 2 alpha into modulus of m plus 1 into dq by dx plus lambda minus m into, okay, modulus of m into modulus of m plus 1 into q equal to 0. Okay, finally we'll replace this m into ml. Okay, so this is the equation, so the second order differential equation in terms of q. If you solve this equation, you will get the solution for q. Okay, how to solve this equation? Yes, it is very easy. What to do is that I am going to apply power series method. So applying power series method, yeah, I'll define like this. In power series method, we'll define the function q in such a manner that q is equal to summation, let me introduce r. R will go from 0 to infinity. R is an integer. It will take value 0, 1, 2, 3, 4, etc. up to infinity, into a r into variable x power r. Okay, let me define a term like this. This is q. Right, now I'll differentiate this once. So dq by dx equal to summation r equal to 0 to infinity. I'll keep this ar as such. X power r, if I differentiate, I'll get r into x power r minus 1. Okay, to get x power r, right, what I'm going to do, wherever r is there you put r plus 1. So this equation can also be written as wherever r is there you put r plus 1, ar plus 1 into r plus 1 into x power r plus 1 minus 1 become x power r. Okay, we can write like this also. Then second differentiation, d square q by dx square can be written as let me take this one, I'll differentiate. So r equal to 0 to infinity ar r into, if I differentiate this I'll get r minus 1 into x power r minus 2, right? I'll get a term like this. You can also make this term as r equal to 0 to infinity. Wherever r is there you put r plus 2, so you'll get ar plus 2, r plus 2, r plus 2 minus 1 become r plus 1 into x power r plus 2 minus 2 become r, x power r. Okay, now I'll take this equation. Let me define this equation as let me give some number to this, say equation number, I think this is a running equation, equation number 9. Okay, I'm sorry, this is equation number 10. Yeah, right, now I'll substitute in equation number 10. So in equation number 10, then if I separate this, I can separate this as d square q by dx square term minus x square into d square by dx square. Okay, d square q by dx square. So in the place of d square q by dx square, I'll write this term, which is summation r equal to 0 to infinity a r plus 2 r plus 2 r plus 1 x power r minus then x square into this minus x square into this. If I multiply this by x square, okay, I'll multiply here x square. If I multiply here x square, x power r minus 2, x power 2 become x power r. So I'll get summation r equal to 0 to infinity. I'll get ar into r minus 1 into x power r. See what I did? I just multiplied x square with the d square q by dx square. So if you multiply this by x square, we have to multiply this by x square. Okay. So here already we have x power r minus 2. X power r minus 2 into x square will give me x power r. Okay. Then the third term, let me write here, minus 2 alpha. Okay, I'm sorry. What is alpha? Alpha is m, right? Modulus of. I'm sorry. 2 alpha is m. So modulus of m into modulus of m plus 1. Instead of dq by dx, I'll write this term, okay, which is something summation r equal to 0 to infinity a r plus 1 into r plus 1 power into x power r. Okay, then the last one, that is plus lambda minus modulus of m into modulus of m plus 1. In the place of q, I'll put this summation r equal to 0 to infinity ar into x power r equal to 0. So we got an equation like this according to power series method. Now what I'm going to do, for this equation to be valid, every coefficient, right, sum of every coefficient of x should be 0. Okay, so suppose I'll take the coefficient of x power r. X power r coefficient is this. The x power r coefficient is this, right? I'll take the coefficients of x power r, right, and that should be equal to 0. If I add all the things, I'll get the value as 0. So what are the values we have? See here. Let me write here. So for this to be valid, all the coefficient of x should be 0. So which is nothing but ar plus 2 r plus 2 into r plus 1 coefficient of x power r minus, here I have ar into r minus 1. Here we have minus modulus of m into modulus of m plus 1 into ar plus 1 into r plus 1. Okay, then we have this term lambda minus modulus of m into modulus of m plus 1, right, into ar. Okay, that should be equal to 0. Every coefficient, if we add, that should be equal to 0. That's the meaning, right? Now let me simplify this further. So here we have ar, here we have one second. I have committed a mistake. One second, let me check it. Somewhere I have committed a mistake. One second. While substituting the equation number 10, I think I made a mistake there. Just give me a second. Yeah, I made a mistake. I'm sorry. Yeah, see here, while writing this term by mistake, I wrote this as alpha. I'm sorry, this is actually 2x. Okay, minus 2x. So I should keep this term, that is the second term. This is actually 2x, so I'll keep the 2 as such. If I multiply by x, for multiplying x I'll take this term. If I multiply by x, so I'll get ar into r. Okay, kindly bear with me. So this is ar into r, x power, if I multiply by x, x into x power r minus 1 become x power r. See, what I'm trying to say is that, see, by mistake I took this as alpha. This is actually minus 2x. Okay, I'll keep this minus 2 as such, the modulus of m plus 1 as such. I will multiply this with x into dq by dx. dq by dx is this. If I multiply by x, I'll get ar into r, x power r minus 1 into x power 1, you'll get x power r. Okay, yeah, so just note down this simple change. Okay, now let me continue here. So here we don't have this modulus. Here we have minus 2 into this is ar. Here instead of r plus 1 I have r into r minus ar into r. I'm sorry, ar into r. That's all. This is the term I have, ar into this r term. Okay, let me rewrite this. ar plus 2 into r plus 2 into r plus 1. Okay, I'll take ar as common. Okay, minus I'll take ar as common, or I'll write once. Okay, minus ar into r minus 1. Here minus 2 into modulus of m plus 1 into ar, and here we have plus lambda minus modulus of m into modulus of m plus 1 into ar equal to 0. Okay, now I'll keep this ar plus 2 term here, and all this term I'll bring it to the right hand side. So if I do so, what will I get is, so ar plus 2 into r plus 2 into r plus 1 will give me equal to, see here, this is negative term, this is negative term, it will become positive, so you'll get r into r minus 1 plus 2 into modulus of m plus 1. Here this will become positive, plus modulus of m into modulus of m plus 1, and this plus lambda become minus lambda. I'll take ar as common. Okay, right? So this is the equation we get. So, or you can write this as ar plus 2 into r plus 2 into r plus 1 equal to this. You can simplify further. How? Let me show you the next page. Okay, this can be written as, if I multiply this, I'll get r square minus r plus here I'll get 2 into yeah, I left one more term here. I'm sorry, this r is there. I'm sorry, I left it, right? I left this r term here, so one r should come here. One r should come here and one r should come here. Okay, yeah. So if I multiply this as this, I'll get 2 modulus of m into r plus 2r plus modulus of m into modulus of m plus 1 minus lambda into ar. I'll write like this. Now this can be further simplified as ar plus 2 r plus 2 into r plus 1 equal to, see here, a square plus 2ab, okay, and this can be written as, you can write this as modulus of m square plus modulus of m. You can separate like this term. If I multiply inside, I'll get modulus of m square plus modulus of m. So this is a square, this is b square, and this is 2ab. So I can simplify this as a plus b whole square. Okay, I can write like this. Okay, see, or I'll do one thing. I'll keep this r square as such, minus 2r plus 2r. Let me simplify this one more step. Plus r plus 2 into modulus of m into r plus here I'll get modulus of m square plus modulus of m minus lambda into ar. Now what I'm going to do is that let me take this term and this term, which is nothing but r plus m the whole square. Okay, a plus b whole square you can write. Okay, and the remaining term r plus m is there, r plus m. Okay, and we have minus lambda term into ar. Okay, or if I take r plus m as common here, okay, we can also write this as r plus magnitude of m as common. Okay, I'll get one r plus term, m term, and we have plus 1. Okay, then minus lambda into ar. Alright, then what I'm going to do, we have just 2 more steps. So some time, I'll take a paper. Yeah, yes, so we got this expression now, right? See, in this expression, see what is the expression we have. Let me rewrite this. So a r plus 2 equal to, I have r plus m term, right, into r plus m plus 1 minus lambda into ar divided by r plus 2 into r plus 1. Yeah, okay, so we can write this into I brought this r plus 2 r plus 1 term here. Okay, yeah, now, and this is what we call as the recursion relation, right? This is the recursion relation. What is the use of this relation? You know very well, we have defined this q, the function q, as summation ar into x power r. Okay, I know x, I know what is x. X is nothing but cos theta. I don't know what's the coefficient. So the goal is to find the coefficient. Okay, if I know suppose a0, if I put r equals 0, if I know a0, then I'll get a2 term. If I get a2, I'll get a4 term, a4 coefficient. If I get a4, I'll get a6. So all the even coefficients can be obtained by knowing the value of a0. Correct? If I know a0, I can find a2, a2, a4, right, a6, etc. Similarly, if I put r equal to 1, suppose if I know the coefficient a1, I can find a3, a5, a7, etc. All odd coefficients can be obtained from this recursion relation. That is the importance of this recursion relation. Okay, but here, before going to do that, let me tell you one information. Listen here, what happens when r approaches very large value? If r approaches large value, see here, ar plus 2 equal to, when r become large, here we have only r term. When r become large, these are all negligible. Okay, so we'll get only r term divided by, here we have r, here we have r, so that become 1. Okay, or I can say ar plus 2 by ar will approach 1 when r become large. Ar plus 2 ar becomes 1, it means all the coefficients become same. After a particular 1 value, all the coefficients become 1, which become unacceptable. Okay, or we can say that when ar plus 2 by ar approaches 1, the function q of x, okay, will behave like 1 minus x square power minus 2 alpha. It will behave like this. Okay, listen, if ar plus 2 by ar approaches 1, okay, the function with the q of x will behave like 1 minus x square power minus 2 alpha. If it behaves like this, what will happen to p of x? See, you know very well, p of x is nothing but 1 minus x square power alpha into q of x. Q of x is 1 minus x square minus 2 alpha, which is nothing but 1 minus x square power minus alpha, or we can write this as 1 by x square power alpha. Here, see, when x already we know when x approaches plus 1 or minus 1, x square become 1, 1 minus 1 is 0, something by 0 is infinity, the function will go to infinity. Okay, the function diverges. We don't want that situation. So what we have to do, we should not allow r value to approach large number. We should truncate the series. Okay, so we should truncate the series. Truncate. Okay, that is, we should convert this infinite series. We should convert this infinite series into a polynomial. Okay, we should convert this infinite series into polynomial. How to do that? That is, we should allow the function to go up to a certain coefficient. Above that, beyond that coefficient, okay, all other coefficients should become 0. Okay, this is possible by making a restriction on lambda. Okay, see, what I'm going to do is that, let me define lambda as, let's say lambda equal to r plus m into r plus m plus 1. Let me define like this. If lambda is this, what will happen? If lambda is this, see, in this recursion formula, after the term ar, if lambda becomes equal to this, then this minus this becomes 0. So ar plus 2, ar plus 4, all the remaining, that is beyond ar, all the coefficients become 0. The function become a polynomial. So we can convert this function into a polynomial by making a restriction on lambda. Okay, lambda, if lambda is r plus m into r plus m plus 1, automatically, okay, the power series vanishes after a certain value of the coefficient ar. Okay, so we should make some condition on lambda. What is the condition? The condition is this. Okay, listen, I'll take this value as L. This is the conventional representation. I'm going to take this value as L. So this can be written as L into L plus 1. This is a standard notation of the L value. So what is L? L is nothing but R plus M. Remember, R starts from 0, 1, 2, 3, 4, etc. Similarly, modulus of M can also be 0, 1, 2, 3, etc. So if R is 0, ML 0, the lowest possible value of L is 0. Okay. If ML is 0, then L can also be 0. So the value of L should be greater than or equal to the modulus of M. Or we can say otherwise that L can take, or ML, this ML can take value. Actually, I am replacing M into ML now. This ML can take value from minus L to plus L. You can say in the other way. Because, see what is M? What is M here? M equal to L minus R. Okay. So R can be 0, 1, 2, 3. So for a given value of L, suppose if I fix L equal to 1, if I fix L equal to 1, if I put R equal to 0, I'll get M equal to 0, plus 1, 0, plus 0, plus 1 or minus 1. If I put R equal to 1, 1 minus 1 becomes 0, ML becomes 0. See what I'm trying to say is, suppose if L equal to 1, then R, if I put R equal to 0, I'll get ML, modulus of ML is 1. Modulus of ML 1 means it can be plus 1 or minus 1. If I put R equal to 1, 1 minus 1 is 0, I'll get modulus of M equal to 0. So ML can take value, okay, from minus L to plus L. Okay, yeah. So these are the conditions we get from this. And if I fix lambda equal to L into L plus 1, automatically the series, okay, the infinite series become a polynomial. Right? Okay, keep this in mind. Now, by making use of this, you can find using this recursion formula, right? You can find the different coefficients, okay, and you can find the even function and the odd function, right? To get the odd function, you should make even functions vanishes. Okay, for that you should make a0 equal to 0. To get even function, you should make odd function 0. So you put a1 equal to 0. Otherwise, the function will diverge. Okay, so that's the point you should note. And to get the even function and odd function separately, it is somewhat time consuming. So what I'm going to do is that in the differential equation, let me go to the differential equation again. Yeah, so this is our original differential equation, 1 minus x square, right? Okay, so in this differential equation, or even in equation number 8, yeah, let me go to that. In equation number 8, what's the equation number 8? Which is nothing but 1 minus x square into d square p by dx square minus equation number 8 or 9, right? Whatever maybe it is, minus 2x into dp by dx plus, now in the place of lambda, I'll put this L into L plus 1. L into L plus 1 minus ml square by 1 minus x square into p equal to 0. Now this is the actual exact representation of associated Legendre differential equation. For this equation, solution is already available. So you can get the solution by using the power series. Okay, it is possible. So what is the solution? I'm going to give you the solution directly because I have already discussed about how to find the even solution, odd solution under Hermite polynomial. So same thing we have to apply here. Okay, but instead of doing that, we can use Rodrigues formula. We have Rodrigues formula for this. Rodrigues formula is available. Let me use that. So now this function p is called, see, we have converted p, actually we have converted q, function q, into a polynomial. Therefore p also become a polynomial. Therefore, since Q become polynomial, P also become a polynomial now. It also becomes like a polynomial, right? Therefore, under Rodrigues formula, the Legendre polynomial, these are called associated Legendre polynomial, PL of mx is now called as associated Legendre polynomial. Okay, associated Legendre polynomial is given as PL of mx equal to, okay, see, actually we should solve, we should use this recursion formula, and we should find the odd coefficient, even coefficient, and based on that you have to find the solution for each L value. Instead of doing that, you can use this Rodrigues formula directly. Okay, the derivation of Rodrigues formula and all are there in a lot of mathematical physics books are there. Okay, you can get all this information from those books. Okay, but I'm going to give you the final answer. What's the answer? The answer is this 1 minus x square power modulus of m by 2. You know very well, this is the function. This will take care of the function when x approaches plus 1 or minus 1. In between, the function will look like this: d by dx whole power modulus of m into PL of x, where this PL of x is called Legendre polynomial. Legendre polynomial. Okay, this is Legendre polynomial of order m, degree L. This is Legendre polynomial. This is associated Legendre polynomial, and this is Legendre polynomial. What is the expression for Legendre polynomial? Expression for Legendre polynomial is 1 by 2 power L into L factorial into d by dx whole power L into x square minus 1 power L. This is called the Legendre polynomial. Okay, so what we should do is, we should find the Legendre polynomial first for a given value of L, then substitute that value here and find the associated Legendre polynomial. Once you know associated Legendre polynomial, you can go to the final solution. What is the final solution? Yes, the final solution is the spherical harmonics. Y is nothing but theta phi. Okay, and y theta phi is nothing but big theta. We have separated like this. Okay, we have separated this function into two, and this function is already known. What is that? This function is nothing but 1 by square root of 2 pi into e power I into ml into phi. This function we know already. What is theta function? Theta function consists of a normalization constant term. Okay, normalization constant that depends on the value of L and M. Okay, into this associated Legendre polynomial PL of mx. Okay, we know very well how to find the associated Legendre polynomial. Okay, and what is this normalization constant? By making use of normalization condition, you can find the normalization constant. Okay, I'm not going to do that. I'm going to give you the final answer. The final answer is this. What's the answer? It is 2L plus 1 by 2 into L minus modulus of m factorial divided by L plus modulus of m factorial. Okay, into this PL of m. Remember, x is nothing but cos theta. PL of m cos theta into 1 by root 2 pi into e power I ml into phi. This is the spherical harmonic function. Okay, I can combine these normalization constant together, and by combining these two, I can write this is 2L plus 1 by 2 into 2 pi become 4 pi into L minus m factorial over L plus m factorial into the associated Legendre polynomial into e power iml phi. This is the spherical harmonic function for the value L and for the value ml. Okay, this is the expression for the wave function for a particle moving on a sphere of constant radius. Okay, so this is the wave function formula. What about the energy? Okay, energy is very simple. Yeah, I have told you that energy let me write here. We have replaced this lambda. We have introduced this lambda by replacing what is called that 2 mu e term. Let me write here. In one particular place, we have replaced that lambda. Okay, instead of the term what is called 2 mu e by h bar square. Okay, so let me rewrite that. I think I don't have it right now. Give me a second. Do I have that paper where I wrote it? Yeah, yes, I got it. Yeah, listen. See, in the last lecture, we have replaced this 2ie by h bar square into lambda. So that is equation number 3 actually. So let me go to equation number 3 to get the energy. So our goal is to find energy. From equation number 3, we know that 2ie by h bar square equal to lambda. And what is lambda? We found that lambda is nothing but L into L plus 1. So we can write this as 2ie by h bar square equal to L into L plus 1. And remember, L can take value 0, 1, 2, 3, 4, etc. Okay. Then A equal to, I'll bring all this term to the right hand side. So h bar square by 2i into L plus 1. This is the expression for energy. And remember, h bar square 2i, everything is constant. So energy depends only on the value of L. This L is a quantum number, is another quantum number. Okay. You can also write this as EL equal to, I'll replace this h bar square as h square. So h square by 4 pi square into 2 become 8 pi square I into L plus 1. So we'll get the expression for energy for a particle moving on a sphere of constant radius, and the potential energy on the sphere, okay, is 0. We have assumed like that. Therefore, this is the rotational kinetic energy of the molecule, of the particle. Okay, and as I told before, this is nothing but rotational constant. So you can also write this as B into L plus 1, where B is called rotational constant of that particle. Rotational constant. Okay. Now, depending upon the value of L, see, L can take only certain allowed values. It can take 0, it can take 1, it can take 2, like that. It cannot take 0.1, 0.2 and all, right? So L can take only certain allowed values. Therefore, energy can also take only certain allowed values. Okay, so EL is quantized. Energy is quantized. Energy for the particle, rotational kinetic energy. This is actually rotational kinetic energy for the particle moving on a sphere of constant radius. Okay, it is quantized. Right? Yeah, this is the point you should keep in mind. And remember, for a given value of L, we have ML can take value from minus L, 0 to plus L. These are the possible value of ML. Okay, for a given value of L, ML can take value from minus L to plus L. So how many ML values are possible? There are 2L plus 1. Minus L to plus L is nothing but 2L plus 1. So we have ML, possible ML values equal to 2L plus 1. 2L, for a given value of L, there are 2L plus 1 ML values possible for the state, for the value of L. Okay, keep this information in mind. In the next lecture, I'll show you the energy